Welcome to Composites Modeling using numerical methods. Today we'll be covering Module 1, Micromechanics, and I have invited Mr. Wei to help us go through a tutorial on how to implement micromechanics in a numerical model. So what is the value of doing micromechanics modeling? So in composite materials, you often have a fiber architecture and a matrix architecture, and those two components together will create properties together that we could represent in a homogeneous manner. So if I know the fiber properties and I know the resin properties and I know the fiber architecture, then I can then determine what the lamina properties are in a homogeneous way. So why is that helpful? So a lot of times you may not have the test data to be able to support the determination of modulus properties, Poisson ratio, and shear modulus, for example. So the homogenization approach allows you to determine those properties as they relate to the fiber architecture for the composite material. So we're really approximating the homogeneous lamina starting from a non-homogeneous composite material that have a unique fiber architecture. So if I were to look at density, how can I get the effective density of the composite if I know the density of the fibers and the density of the resin? So or the matrix material. With that information, I should be able to find the density of the composite as a whole, the homogeneous density. In this case, the density of the composite can be determined as being equal to the density of the fibers times the fiber volume fraction of the fiber plus the density of the matrix times the fiber volume fraction of the matrix. Fiber volume fraction is a ratio of the volume of the amount of fiber that we have divided by the full volume of the composite. And so it's typically a value that could be between 0 and 1. Typical fiber volume fractions will be in the 0.7 range. So then, therefore, the fiber volume fraction will be 0.3. Some books use uppercase for volume. In this case, lowercase is used. But the important thing is to understand the concept. Here, you can see that we have used uppercase for V to then describe what the fiber volume fraction variable is. But again, different books use different convention. The important things to note here is if you know the fiber volume fraction and you know the matrix fraction, volume fraction, you can determine the homogeneous density of the composite. Very similarly, you can determine information if you know the weight fraction of the fiber and the weight fraction of the matrix. You can also determine the density of the composite too. So here's an example. A glass epoxy lamina consists of 70% fiber volume fraction, but the fiber volume fraction can range, anywhere between 50% to 80%, right? And so, but in this example, we're choosing 70% for glass epoxy, and we want to determine the density of a single lamina. We also want to determine the mass fractions of the glass and epoxy. And then we want to determine the volume of the composite lamina if the mass is known. Here are typical fiber properties that you may find for a particular 3 different fiber systems: graphite, glass, and aramid. These properties can be found also through specs. For example, if I'm interested in an IM7 fiber, carbon fiber, I can find the IM7 spec in the vendor's or supplier's website. Typically, the property will be provided as such. So I'm looking at the fiber properties, and it will provide modulus material information, the Poisson ratio. Typically, the Poisson ratio of graphite materials will be in the 0.3 range, but most typically you'll be somewhere between 0.2 and 0.35 for most materials. You can also, you will be given the transverse Poisson ratio. Typically, the axial and the transverse will be similar to each other. The specs typically provide the axial shear modulus, the coefficient thermal expansion, and so forth, including specific gravity. Typical matrix materials here, what I'm showing is epoxy, aluminum, and polyamide. You can see here, these are units of GPa or metric system. But the important thing to note is that you can obtain also very similar properties for the material system that you are looking for. So given the epoxy properties, given the fiber properties, I can then, if I know the properties of the fiber and the matrix, I should be able to get the homogeneous properties of the system in question. So in this particular example, the density of the lamina can be determined because we know the density of the fiber and the density of the matrix using the data that's provided here in this page, and also in this page. And I can determine that because I know the specific gravity. So from there, I should be able to tell you the density of these two materials. So we found the density from specs. And I know that the volume fraction is 70%, so therefore the volume fraction of the matrix is 30%. So I can just plug in the numbers directly and find that the composite density is 2,110 kilograms per meter cubed. I can also determine the mass fractions of the glass and epoxy. So I can do that because I know the density of the fiber. I know the density of the composite because I just found it here in this step. I know the fiber volume fraction. So therefore, with this multiplication, I should be able to determine the weight fraction, which is 0.83. And then very similarly, I can find the matrix fraction, which is 0.17, the weight fraction. We can also easily determine the volume of the composite lamina. If I know the weight fraction, the weight of the composite, which was given as 4 kilograms, then if I know the density of the composite, I can also determine the volume as well. And you can see that's provided here. And then if you know the volume of the glass and epoxy, if you know the volume of the composite and you know the volume fraction of the fiber and the matrix, it's a simply multiply these two variables to get the volume of the fibers and the volume of the matrix. So in real applications, composites do contain a void. I invite you and encourage you to look at one of the first lectures from the channel. And I give an example of how to treat voids in this type of calculations. And there are two ways to calculate voids and the void fraction. A good void fraction in a composite system is 1%. That's what you want to shoot for or less. But void fractions can decrease the strength. If the void fraction is very large, the matrix dominated properties will be impacted by that. And that level porosity can be detrimental in the performance of the composite in high performance applications. I also want to point out that you can calculate the void fraction looking at various techniques. There's one that's called the burnout test. You're burning out the resin. And using that information, you can determine um, how much weight is left on the fibers, what original weight you have from the composite. And with that information and the specs, you can determine the void fraction. That's one technique. The second technique is to do a cross-image microscopy. Looking at the cross-section, you can identify voids and then calculate area, and then from there, try to estimate the void content. How to then determine the elastic properties? I know the modulus of the fiber, I know the modulus of the matrix, and those are provided But what is the modulus of the homogeneous lamina? So really what we're looking for here is, I know the modulus of the fiber from specs, the supplier specs. I have the modulus of the matrix. Question is what is the homogeneous behavior? And so they are four formulas. They are approximate formulas, but they are effective at doing and providing an estimate of what these properties could be. The equations, all they use is a fiber volume fraction and the matrix volume fraction. Given the fiber modulus and the matrix modulus, I should be able to calculate the modulus in the one direction. Very similarly, I can determine the modulus in the two direction using this formula. So that's transverse to the fibers, as you can see here. So that's quite clear there. And I can also calculate the Poisson ratio. The Poisson ratio in the 1-2 plane. And so what is this Poisson ratio? The Poisson ratio, what it really means is the strain caused by loading in the one direction divided by the strain that has occurred due to loading in the one direction. In fact, it's the opposite of that. So let me repeat it again. So the Poisson ratio 1-2, what that means is that is a strain measured in the two direction. I apologize. Due to a load applied in the one direction. So you take the strain in two direction, divide that by the strain in the one due to the load applied in one direction, and that will give you the Poisson ratio. But you can measure that indirectly or predict that indirectly, because if you know the fiber volume fraction and the fiber volume fraction of the matrix, you can then estimate this Poisson ratio. It won't be perfect, but it is an estimate, and it is possible to do that. This very similar manner, we can calculate the shear modulus, which is a prediction as well, and then determine, using information on the fiber volume fraction, the matrix volume fraction, the shear modulus of the fiber, the shear modulus of the matrix, I can then estimate this shear modulus. And that information is not completely sufficient, but it is a good start. And it may not be perfect, but it is a good start. So we can do an example here quickly, but for the same example I showed earlier, I can calculate the effective modulus in the one direction. I know the fiber modulus from specs and also the matrix modulus, so I can then determine the effective E11. So fairly simple process there. You can see the formula there. The same thing we can do for the fiber volume fraction, for the fibers and the matrix. I can use that information to estimate the modulus in the two direction. Very similarly, again, I can get the Poisson ratio as well, and you can see the calculations here. To the shear modulus, if I know the modulus of the fiber and the Poisson ratio of the fiber, I can estimate the shear modulus of the fiber, and that is using this formula. I can do the same thing for the matrix. I know its modulus, I know its Poisson ratio. I can use this formula to calculate or estimate the shear modulus. If that's provided to you, you can go straight to this calculation. But if it is not provided to you, you may have to do this calculation. And then through this procedure, I can get the shear modulus of the homogeneous lamina. So what are we trying to attempt to do next? What I want to do is to illustrate for you how you can estimate properties using a more advanced technique, which is using finite elements. With finite elements, what you can do is to model a representative unit cell. And that unit cell will contain the fiber architecture of interest, and you can use that information and apply periodic boundary conditions to then determine the properties of the composite in a homogeneous way. There are many techniques that exist that can do that. Codes that have done it in the past are TextCAD, but there are other types of modeling software that can actually do that for you as well. This representative volume element that we're talking about has been used in industry to really simulate what the modulus could be for to get the properties for a representative volume element. You can get the properties, and in this case, we're going to be examining a 1 by 1 unit cell that has fibers here. They're in a 70% fiber volume fraction. And the idea here is to then determine the effective properties using a different method, but not using the hand calculations as showed here, rather using a more sophisticated method. In reality, at the end of the day, it's going to be important to characterize the properties through a test program to really validate your modeling that you have done. But this can be very helpful in the process of modeling for supporting conceptual designs, for example. The good news is that properties such as the E11, the modulus in the one direction of the composite, the modulus in the second direction, the Poisson ratio, and shear modulus, both can be found through either testing that has been done historically or through testing that you do as a support of a program. So I do want to move and introduce you to Mr. Wei, who has extensive expertise in the modeling of composites. We'll be providing you the files so you can be successful in doing these simulations. With that said, over to Mr. Wei. Thank you so much, Mr. Wei. I appreciate your time.
Hi everyone. Today I'm going to show you how to use abacus to calculate the effective modulus of composite material. Here is an example, the glassy epoxy laminar with 70% fiber inside. In abacus, we are going to create a unit cubic size with 1 by 1 and depth is 1. And also the fiber is with the radius 0.334 so that the volume ratio will be 70%. The material property for the fiber and the epoxy are listed here, the Young's modulus and the Poisson ratio. And we are going to calculate the modulus, the E11, like along the depth direction, E22, and also the shear modulus. Okay, let's start. We open the abacus. So here I already built the model. Then I will tell you step by step how to run this simulation. First, we create the model. As we are going to create a 3D model, we use solid shape and use extrude one. We can create first create a rectangular one with 1 by 1 size and depth 1. And then we are going to partition it to create where the fiber is. The fiber is circle. We click the center point, and then 0.234 is the radius. Then we can just copy it. And then do another copy. There's another 2 in the bottom. Then we just do a symmetric change. Okay, we're finished. Then we're going to extrude this fiber along the depth. So we select this one, the extrude oscillate the edge. We select all the edges. Click OK. Then extrude along the direction. We want to extrude along the depth direction. Then that's done. So the geometry is created. The next step is to input the material properties. So we are going to create 2 material. One is fiber. The modulus is 85. Poisson ratio is 0.2. The elastic property. And also the epoxy, that's the modulus is 3.4. The Poisson ratio is 0.3. Then we assign two material properties to the parts we have built. So the fiber is this 5 region, the circle region, and then the epoxy is the remaining parts. Then we just assemble the model and then create a step. We are going to use the linear static method. We can just use the default setting, no need to change. Then it goes to the most important part, it's interaction. So because it's a composite material, we need to make some locking to make the surface to move together so that we can calculate the effective modulus. So in the case 1, we are going to calculate the modulus along the depth direction. So we want at this surface, we call it front, to move together in z direction. And this surface, we call the right one, that move together in the x direction. Also at the bottom surface, they move together in the y direction. So I create 3 reference points. And if you want to create a reference point, you can click Choose and then click Reference Point. Then you input coordinates. So these 3 points is the coordinates is 0, 0, 1, 0, 0, 2 for reference 1, 2, 0, 0 for reference 2, and 0, 2, negative 2, 0 is reference 3. Once I create these 3 reference, I also create a set for these 3 reference. Then you can see reference 1, I set is RF1 set. This is reference 2 set, reference 3 set. Also, I create a set for the front surface, the right surface, and also the bottom surface. Then I'm going to set some constraint to let this surface to move together. So to make it, I use the equation constraint. So to create the equation, you can just click create a constraint. And then choose the equation. Here. Then let's see how I build it. So actually, I make the surface 1 constraint with the reference point 1 in the degree of freedom 3. Then I let them to move together, so coefficient is 1 and negative 1. Also, I make the remaining, the reference 2 with the surface 2 move together in x direction, which means the degree freedom of 1. So that in x1 direction, they don't have any gradient. Also, for the reference 3, the bottom surface, I let them to move together in y direction. Okay. Then after we set this, we can set the boundary condition. For boundary condition, we are going to load the front surface. So we can set the back part, this surface, not move, or we can see the symmetry steady. And at the top surface, this surface and the left surface, we can just fix in the y and x direction. So we can see how I set them. So for the left one, I don't let it move in the x direction. For the top one, I don't let them to move in the y direction. And also I set the back part, the symmetry in z direction. So then for the loading, I apply the displacement control at this point. Because this reference point 1 is constrained with the surface 1. So once I apply the displacement at this point, that means I apply the displacement at this whole surface. They will all together move point 1 in z direction. Then I'm going to mesh it. So for the mesh, we need to be very careful. First is the mesh control. We want to use this sweep, text sweep, that the mesh will be the same along the depth direction. Second, we need to control the seed. So you can see at the edge, the top edge and the bottom edge, I set them as the same set. That is very useful for later periodic boundary control. And also I make the circle a little bit finer. The left and the right, this mesh set control should also be the same. The same, I mean, should be point to point. Each point should be at the same location. Then the mesh type, we use the plane stress, 3D stress, and not plane stress, use the 3D stress. And then we use the linear. We can use the reduced integration. If there's no hourglass, that will be okay. Okay, we have set all. Then next question is what we want to get. Actually, if we want to calculate the effective modulus, we need the force and displacement. We already get the force, we already get the displacement, then we need the force. So we go to the step. Then in the history part, we want the force, reaction force at reference point 1. So we request the reaction force. Actually, we just need the reference force at the z direction, but I just click it all because later we need like a reference 2, then they may need a reaction force as the x direction. Then we only need the set for the reference 1. So here we change it to set at point here. After we all done this, we can run the job. Go to the job, we just run it. So already run it. Then let's see the results. Okay, here is the result. We can double check whether everything is correct by checking the displacement control. So you can see at this part, we want this surface move together with point 1. So it is exactly show what it is. And the next step is we want to see what is the reaction force. So we'll go to the history output, then click the reaction force 3. Then we click plot. So here is the reaction force as a function of time, which is also a function of displacement. If we want to know the data, we can click the editor manager XY data, and then click edit. Then it will pop out what the value it is. So it's a 6.05175. Then we can calculate the effective modulus E11. So what is the effective modulus E11? That is the force we get divide the area that is stress. Area is 1 by 1. Then divide the strain. The strain, because the depth is 1, so the strain actually is it's the 0.1 divided by 1, so it's 0.1. Then finally we get 60.5175 gigapascal, which is same as our calculation, hand calculation. Why the results are same? Because in the abacus simulation and the hand calculation, the assumption is the same. In this hand calculation, they assume that the fiber and the epoxy will move together, which means the strain of the fiber and the epoxy are the same. So it's equivalent to the two spring that move together. Then the effective modulus is the fiber modulus multiplied the volume plus the epoxy multiplied volume, which is the same as our simulation. Then next, we are going to calculate the E22, which means the force is in this x direction. So as we already built model, actually we just need to change a little bit. Then the easy way is we just copy the model, then rename it. Then as I already copied it, so we directly go to the E22 model. See how I change it. So for this case, we want to apply the load at reference 2 along the x direction. So for the boundary condition, the left part, this part, we still keep it. The top part, we also still keep it, don't need to change. Then the x load is the load we want to use. So we just use the displacement control, the 0.1 at reference 0.2. And then for the previous load at reference 0.1, we don't need it. So just delete, inactivate it. Then for the symmetric boundary here, we just also keep it. Then for the interaction, we don't need to change anything. We also have needed to reference 0.1, and we also want this surface to move together in the z direction, and also this three surface to be flat. Another thing need to change is the output. So for the history, now we want the reaction force at reference 0.2. So we just change the site from the reference 1 to the reference 2. Then click OK, then we can run the case. So now let's see the results. So first, let's double check whether our setting is right. We just check the displacement control. Then we see the control, there's 0.1 displacement at this surface. Okay, that's right. Then we are going to say the reaction force. So reaction force we want to at in the x direction. So it's 1. Then we check the value. It's 1.428. Then we calculate the effective modulus. So that is listed here. The force divided by the area divided by the strain. So it's 14.2814, which is sort of a little deviate from the Han's calculation. So the main reason is the assumption between Han's calculation and our Abacus simulation is different. For the Han's calculation, they assume the fiber and the epoxy, the stress on the fiber and the epoxy are the same. So the rheological model is 2 spring, they are parallel, and then the stress will apply here. So the modulus will be the stress divided by the total strain, the strain of the fiber plus the strain of the epoxy. Well, in the real case, actually, we can say it's totally different. If we create the model like this, if we make the stress distribution, we can see the stress first is inhomogeneous distributed. So it's not a simple 2 spring parallel together. And also, because the fiber geometry, then the deformation of the epoxy is also not homogeneous. So which means the effective modulus E22 related to the volume fraction, also the distribution of the fiber. That's the main reason why the Abacus results is different from the Han's calculation. Then we are going to double check the this Poisson ratio. For the Poisson ratio, actually we can check through the E11 loading. So when we load it, oh, sorry. we can check it by this. So when we load it, we can use the displacement or string change in the lateral versus the longitudinal. So to check this distance, we click this current information and then click distance. We select 2 points. Then it will show at the bottom how much displacement it is. Then we calculate the Poisson ratio, which is 0.2 negative 0.2 divided by the longitudinal string is 0.1, which is 0.22. It's very close to the hand calculation. Okay, the next is a case 3. We are going to calculate the shear modulus, G12. So still we copy our E22 to the G12. Then we just need to change the boundary condition and the constraint issue. Other, we just keep it the same. So for the G12, the shear modulus, we will apply the load at reference 1.1 and then let this surface move together in the x direction. Then the boundary condition will be changed a lot. So first, the bottom, we still keep a symmetric. Oh, sorry. This one, we can keep it symmetric or just fix it. So here I just fix it, don't let it move. And then for the bottom one, as it's a pure shear, we don't want it to move in the y direction, only shift in the x or z direction. Then we fix the y direction. Also, for this front one, top one, we also fix in y direction. You see highlighted one. Then we inactive the two load, apply the load at reference point 1 with displacement control. We just set a point 1 for example. Then we go to the constraint. Then constraint parts, we need to change something. First, we still keep the surface, this front surface in the direction, they are the same. Because it's pure shear, we don't want it to have like a zigzag or something. We want this flat, surface to be flat. So we constrain in the z direction. Then another is we want all these points move together in the x direction. And then we inactive the other two constraints because for pure shear, this surface will be tilted. So we cannot lock in the x direction, same as this part. And for the bottom one, we already set the boundary condition, so we don't need the additional constraint. Then we can run the cases. Okay, here is the results. Oh, also don't forget, I forgot to tell the output. The output we still want the reference point 1 because we apply the displacement. We want to calculate the reaction force. We want this is 1. Then we can see the results. Okay. Now to see clear, we can show here displacement in x direction. So you can see here it moves 0.1 and then we request the reaction force. Reaction force we want x1 direction, which is 1.01. Then we are going to calculate the effective shear modulus. We go to here. So we calculate it by 1.1 divided by area divided by string. Then we got 10.1361 gigapascal. So this value is far away from the Hans calculation. The main reason is for this hand calculation, they have assumption that they assume that the fiber and the epoxy they have the same shear, like same shear string. But in actual case, they are different. And there is a reference to tell such equation may underestimate the shear modulus. Here I list a link. If we open it, then we can see this is the equation that we got. The equation 13 is the same as this one. Then they said this relation, as the experiments show, tends to underestimate the value of G12. And there's a modified equation, that equation 14, that I consider more. So here we are going to use the glass, this value. If we recalculate it, the shear modulus will be 9.27, which is very close to our simulation results. Okay, this is general how to calculate the effect modulus. But there's one point we need to know, is there's some may have some misleading about the boundary setting. So you can see for this boundary setting, we want this, our simulation is a unit. So that means they have infinite units can be applied together. So which means the nodes at the edge should be the collinear with nodes at the edge. Like these two nodes will be the collinear. But if we check the coordinate, they actually are not at the same z coordinate. Then we need to set periodic boundary condition to make them like kind of collinear. To make it, if you search online, there have many package, the Abacus package, but it's not free. So I just simply write a Python code, then you can free to use. But there is some steps you need to do. First, you are going to create two sets. So if you go to assemble, go to set. So first set is the node set. You need to exactly name it as L. So if you view in this XYZ view, then you select all the nodes at the left boundary, and then create sets as L, and then select all the sets at the right, name it as R. How to create a set is just that, create, then create a node, okay? Then you go here, go here. Then you can select all the things. Then that's how you create it. Okay. After you've done this, you go to the job. You write input. Okay. Then you open the Python code that we uploaded. It's called input regenerate. You just open it. And then what you need to change is two things. First is a file name. File name is the input name, which you create the here. It is. Second is called count element number depth. So it means how many elements in this direction. In this direction. So here we have 1, 2, 3, 4, 5. Oh, maybe I say something wrong. I mean the nodes in depth direction. So it's 1, 2, 3, 4, 5. So there will be 5. So here you just put 5. Okay. Then you can run it. So here I use the Python, so I can run this one. Also, you can use the txt file to modify these two things. You only need to modify these two things, and then use other things. You can use the MATLAB or use other shells to run the Abacus scripts. After you run it, you will get this is PBC, the periodic boundary condition. Here, I create the periodic boundary condition automatically. All listed here. Then, after you get this, you go to find your G12 input. You copy the one and then create a new one. Then you go to the new one. So here actually is some keywords and then what you input. You scroll down to the end and then before this equation, you can write this in. Include the star, include input pvc dot input file. Okay. Then you save it, close it. You go to the Abacus, click File, Import Model. Import model and input file. Then you double click the G12. So I already import this model. So we can look at what this looks like. So when you import it, you can check what I have done and what this that Python code done. So actually the Python code create a lot of constraint. This is all the equation. Now we just click one of them. So actually it make the point to the point collinear that the displacement at this point equals the displacement in x direction of this point, the corresponding this point. Also, in the y direction, this is all the x direction. Let's see any x direction one. Okay, in z direction, I also made them to move together in z direction, so that this will be a unit cell, unit model. That means you can implement multiple infinite units to represent the composite material. After you check this all is right, then you go to job. You run it. Before run it, I highly recommend you rename the job name. Then let's see results. So now you can see this point have same movement as this point, which means you can create another unit here, and then another one, infinite one. This model is represented composite material units. Then we check the reaction force. Then you can see the reaction force is 1.44. Then we calculate the modulus, which become the 14.4, higher than that's the Hence calculation, because we have more constraints, so that make the model more stiff. So that is how we simulate the effective modulus for composite material. We cannot say which one is more correct. The most important is you need to know what assumption you have made to make the simulation. Whether your material will like move together, whether you want the material have like deviation, or whether material have the same shear deformation when you apply the shear force or shear displacement. It really depends on your assumption, and really depends on your material and the like glass fiber distribution and also the volume fraction. I hope this video can give you a sense about the composite material modeling. All the input file and the Python code will be available online.